You can start recording. So welcome everybody to the second presentation today. This will be given by Samuel K. Degalia from the University of Oklahoma in the US. And he's talking about impact of flow-dependent and static observation error estimation for frequent assimilation of thermodynamic profiles on convective-scale forecasts. So Samuel, the floor is yours. We're looking forward to your presentation.
Awesome. All right. Thanks for the introduction and thanks everyone for being here. Like you said, my name is Sam Dejoy and I'll be presenting a recent project I've been working on that focuses on flow-dependent estimates of observation errors for the frequent assimilation of thermodynamic profilers. Before I move on, I want to acknowledge a variety of the people who helped us with this work, including my co-author, Dr. Xuguang Wang, along with Dave Turner, other members of the OU Map Lab, and the Pecan data providers. So a little bit of background information to start with. The observation error covariance, denoted by R, partially controls the weight assigned to an observation when it's assimilated. This error is composed of both static and flow-dependent components. And by flow-dependent, we mean errors that change depending on the meteorological feature being sampled. So remote sensing instruments typically feature strong flow-dependent to their observation errors, such as for these satellite-based radar observations shown here. You can see that representation errors are larger in certain parts of the storm. Unfortunately, operational DA centers often assume constant observation errors or use static methods to estimate the errors that don't depend on the flow. And we've shown in some of our recent work that such methods can lead to either overestimated or underestimated observation errors, which can degrade the forecast quality, sometimes to the point where it'd be better to not assimilate the instrument at all. One way around this problem is through using methods that estimate flow-dependent observation errors, and there are two main types of these. First, there's adaptive observation error inflation techniques, which, for example, can inflate observation errors based on the innovation. And then there are also methods that directly estimate unique observation errors for each time. One of those include the Degalia et al. Diagnostic, which I'll be coming back to later in this talk. However, most previous work that evaluates flow-dependent observation errors typically looks at coarser global models or focuses on satellite observations. Relatively little work has looked at the impact of such methods on finer scales, such as the convective scale, where representation errors become increasingly large. So the main objective of this work will be to explore whether we can further improve the benefits of assimilating remote sensing data on the convective scale using flow-dependent methods to estimate R. And we'll be focusing on assimilating high-frequency thermodynamic profiles collected by AERIs during the Pecan field campaign in 2015. So I'll be presenting results where we assimilate the AERIs using two main sets of methods and a static and flow-dependent implementation of each of those methods. So first up, starting with a method that's based around inflating AERI retrieval errors to account for systematic errors. So the static inflation is given by this equation here. It involves inflating these retrieval errors by this term on the right-hand side, second term on the right-hand side, which accounts for representation errors and is derived from radiosondes. So I invite you to read our 2019 paper for more information on this. But the main point here is that this error inflation is constant in time and is therefore not flow dependent. To show how we adapt this error inflation into a flow-dependent method, I need to provide a little bit of context on a common problem associated with AERIs. So here are some time-height cross-sections. Actually, let me show my pointer. There we go. Here's some time-height cross-sections of AERI retrievals collected during Pecan. On the bottom is the retrieval effective vertical resolution, which AERI outputs, the AERI retrieval outputs for each observing time. This is in units of kilometers and measures the vertical smoothing used to compute the observation. So larger vertical resolution indicates more smoothing, which is kind of the opposite of what you normally expect with the term resolution. But anyways, these cross-sections show a problem with AERIs that sometimes occurs just below cloud base, indicated by the white curve. You can see that vertical resolution sometimes becomes very large, about this 500 meter thick layer below the cloud, indicating significant vertical smoothing. This has been explained as a problem with the retrieval algorithm separating cloudy emission from the total measured emission. And if you look at the retrieval errors, while they do increase with height, they don't increase nearly as rapidly as this vertical resolution. That means the retrievals are showing significant vertical smoothing just below the clouds, and that the resultingly large representation errors aren't captured by our retrieval errors, and also wouldn't be captured by our static error inflation. But this doesn't occur at all times. You can see at earlier parts of this cross-section that the vertical resolution is fairly standard. So one way to account for this flow-dependent problem is by including the vertical resolution profile in our error inflation. So here's our previous static inflation with a temporally constant error inflation, and then here's our new inflation, which includes this gamma term, which is the vertical resolution, which varies in time. And this allows us to adaptively inflate observation errors to account for potentially problematic observations just below cloud base. Next up, we also perform a set of experiments based around the de Rosier diagnostic shown here, and this estimates the full observation error covariance matrix based on a product of the innovation in analysis residual vector. But to get to the final observation error, we also have this pesky expectation operator. So for our static implementation of the de Rosier diagnostic, we collect every cycle used in our 2020 paper, which assimilated AERIs over 130 cycles. This gives us a very robust estimate of R, but it's constant and not flow dependent. It only varies by site. To actually generate a flow-dependent estimate using the de Rosier method, there are a few options. You could either use very high-resolution observations and average over those, or you could use an ensemble and average the product of those vectors of your ensemble. And we actually do both, since the AERIs are such high temporal resolution on the order of minutes, we're able to collect multiple retrievals for each cycle and site, and then we also average over 40 ensemble members, which gives us a fairly robust estimate of R for each cycle and time, or each cycle and site. One thing I should mention is due to the limitations of the serial E and KF we're using, we're only able to assimilate the observation error variance instead of the full covariance matrix. So to account for those off-diagonal terms, we apply this multiplicative inflation C, which other studies have shown to at least somewhat cover the off-diagonals. So here's a list of the experiments I'll be showing that assimilate the area retrievals using different methods to assign their observation errors. These include the ARIOE inflation methods and the de Rosier diagnostic methods, and I'll be showing a static and flow-dependent experiment for each method. In addition to those, I'll also show a baseline no ARI method so that we can make sure we aren't overinflating observation errors to the point which they have no impact. And then a final experiment called MAX that assigns the maximum observation error between ARIOE FD and de Rosier FD to utilize benefits of both. And MAX also accounts for potential cases where de Rosier FD might estimate too low of an error, which can occur if the innovation or analysis residual at that cycle are near zero. So these experiments are going to be evaluated for a nocturnal MCS from Pecan. The evolution of that event is shown here. This wasn't a severe MCS, but it is fairly typical of nocturnal MCSs over the Great Plains. It eventually featured this standard leading convective line and trailing stratiform structure. And for this case, I'll be assimilating AERIs from these 6 different sites. And just real briefly, overview of the DA and forecast system, which is centered around a GSI-based ensemble common filter paired with Warfare W. So the flow chart on the bottom shows the design of our cycle DA system. But in total, we performed 13.5 hours of data assimilation, first on an outer 12-kilometer domain, and then an inner convection allowing 4-kilometer domain, where we also assimilate radar data, before initializing forecasts from 10 ensemble members to capture the MCS. So with all that out of the way, I can finally jump into some results. First up, looking at mean and standard deviation of the error profiles produced by each method. By looking at these profiles, we can pick out a few main findings. First up, we see that the mean error profiles are similar in magnitude, but with shape differences. Mainly the ARIOE methods in red produce error profiles that increase with height throughout the entire profile, while those based on the de Rosier diagnostic are typically larger in the boundary layer. This means that our innovation and analysis residuals are larger near the surface and possibly indicate uncertainty due to local circulations. But the biggest impact from using the flow-dependent methods, given by the dashed lines, come from the right plot, which represents the standard deviation of all the different error profiles we assign. Basically, we see much more variability when using the flow-dependent methods of ARIOE FD and de Rosier FD. And this increased variability more closely matches observed error statistics derived from radiosondes, which are shown in black. So this is a good result. This means that we're getting more variable observation errors when using these flow-dependent methods. Now that we've seen the error profiles, I can show what happens when we actually assimilate area retrievals using these different methods. So these are neighborhood ensemble probability plots with observed reflectivity overlaid in black. Fraction skill score is also shown in each plot, but I'll come back to that in a little bit. At first glance, you might think that the simulated MCS look fairly similar between each experiment. However, there are a few main areas I want to focus on where the observation errors have large impacts. First, looking at this region of spurious convection to the north of the MCS. Zooming in on that, you can see that no AERI, and to a slightly lesser extent, AERI-OE, using the static inflation method, they both generate this north-south oriented band of spurious convection. But compared to those baselines, using the flow-dependent AERI-OE or either of the de Rosier implementations, both work to suppress that spurious convection, increasingly so to the point where de Rosier FD removes a large percentage of that convection. And MAX, which utilizes both AERI-OE and de Rosier FT, also suppresses a lot of that convection. Now, to understand why the new experiments suppress that convection, I want to compare a single member between AERI-OE, which simulates a lot of spurious convection, and MAX, which simulates relatively little. We find that this north-south oriented band of convection corresponds to a north-south oriented band of increased mid-level moisture at about 850 millibars. This additional moisture also manifests as a band of increased CAPE that extends into southern Nebraska, which supports the development of this convection. But comparatively in MAX, which uses those flow-dependent methods, the northern extent of that moisture is limited. We have less CAPE and overall less convection that develops to the north of the MCS. So to try and trace this elevated moist layer back and understand what exactly is changing in the observation errors to modify this, I'm going to show a set of retrievals assimilated from FP3, which is just upstream of this moisture. First, just looking at the observation and background profile on the left panel, you can see that the area observations assimilated from this cycle are much moister than the background, thus leading to the model being pulled to the right in the analysis, which makes sense. However, if we compare against a co-located radiosonde that was taken at the same time, we see that the area retrievals are likely too moist and that actually the background was closer to being correct. So if you turn and look at the observation error profiles, we see that the AERI-OE method, the static error inflation method, produces the largest observation errors and as such provides the largest weight to these very moist retrievals. And that in turn ends up adding in more moisture and eventually leading to that spurious convection. Conversely, the other observation error methods generally de-weight these retrievals, and the largest de-weighting comes from de Rosier flow dependent, which is directly proportional to the innovation and analysis residuals, which are very large, above 850 millibars. So because of those large innovations, de Rosier FD de-weights these moist retrievals and eventually reduces the extent of that spurious convection. Now, if we shift our focus from the spurious convection into the actual MCS itself, we can also identify another region where the methods are improving upon AERI-OE. So looking at this circled region, we see that AERI-OE compared to no AERI is actually degrading a lot of the precipitation in the trailing stratiform region of the MCS. And this degradation is primarily what leads to AERI-OE producing the lowest skill of all the 6 experiments. And this shows that using a static inflation technique to estimate observation errors can actually be worse than just not assimilating that data at all. Now, when using AERI-OE FD or either the de Rosier experiments, we see increased probabilities for those trailing stratiform regions and overall increases to the skill. And the same occurs in MAX. So on the last slide, I highlighted some example profiles to show how de Rosier FD can improve parts of the forecast. Now I want to focus in on AERI-OE FD, the flow-dependent inflation method, to show how this improves the trailing stratiform region here. So these retrievals were assimilated almost directly underneath the MCS during the final DA cycles on our 4-kilometer domain. We see here that instead of a moist error in the retrievals, these retrievals show a dry error compared to radiosondes. And if we, again, look at the baseline AERI-OE method, the static inflation method, it assigns fairly small observation errors, which gives large weights to these dry retrievals, which ends up being the main driver of what's weakening that trailing stratiform region. Now, if we look at ARIO-E FD, this profile features very large vertical resolution, especially once you get below cloud base. And this is what I mentioned earlier, where the retrievals sometimes have the systematic error where beneath clouds, they tend to smooth through features a lot. So because with our flow dependent method, we're able to account for this vertical resolution, this time varying vertical resolution, we see a large increase in the error for ARIO-E FD, which ends up again de-weighting the retrieval. And in this case, it ends up adding in more moisture in ARIO-E FD and improves that trailing stratiform region. So finally, I also want to mention one last impact we saw from assimilating AERIs using these novel methods. And this impact is related to the orientation of the MCS. So if I overlay the strongest observed convection in these blue contours, we can see that the de Rosier experiment, especially the flow-dependent de Rosier method, produces a much better match to this contoured region. Max also shows similar improvements, and along with simulating higher probabilities within the eastern portion of the MCS, shows a very, very good match to this observed MCS. So along with suppressing the spurious convection and simulating a better trailing stratiform region, this de Rosier flow dependent and its associated MAC experiment simulate overall the best looking MCS and produce the highest values of fraction skill score. And when we combine those methods, the ARIO-E FD and de Rosier FD, we get our highest skill, indicating that there are individual benefits for each set of methods that can be both taken advantage of when you combine the methods together. So that wraps up everything I had time to discuss today. If you want to see more, I invite you to read our paper. But in summary, we tested two groups of methods, one based on inflating retrieval errors and one based on the de Rosier diagnostic. And we also tested a static and flow-dependent implementation of each method. We find that the flow-dependent methods better represent observed error statistics, especially that increased variability in the error profiles. Compared to a static inflation technique that actually degraded the forecast quality, the flow-dependent implementations improve the forecast such that we see an overall skill increase when assimilating the area observations. And one main takeaway here is that the results indicate that observation errors are actually very important and deserve a closer look, and that we shouldn't just assume that previous methods, be they constant errors or static inflation methods, are good enough. I didn't mention this earlier, but I want to note that all the benefits we found resulted when increasing observation errors or de-weighting the observations in comparison to our baseline static method. Finally, I should also mention that the ARIO-E methods this ARIO-E inflation can really only be used for area retrievals since it relies on that vertical resolution, but it does serve as a proof of concept to show that flow-dependent methods are impactful and can improve forecasts of convection. But going forward, we're primarily focusing on the de Rosier method currently for assimilating ABI all-sky radiances. And in the future, we also want to use more advanced DA methods that can assimilate the full R covariance diagnosed by the de Rosier diagnostic instead of only estimating the error variances. And with that, that's all I have to say, and I'll take any questions if there's time.
There's time, Samuel. Thank you very much for this nice presentation. Very interesting results, and it nicely shows how important flow dependence is for convective-scale data assimilation. And we already have a few questions in the YOPAD. The first one by Jemima Baird. So these results look really compelling. What is the computational cost of computing the flow-dependent terms? So this was also something I was thinking about. And would you do, so if you can refer to that and I can continue afterwards, yeah?
Sure, yes. So the ARIO-E inflation has no additional cost computation, but the de Rosier method does. So I didn't show it here, but we actually do an iterative technique, which has been recommended in the past because de Rosier requires an analysis residual to calculate the observation error. You have to perform a cycle, get an analysis, and then compute your de Rosier diagnostic, and then re-perform that cycle using that new error. So this actually doubles the cost of the assimilation. So yeah.
So did you think about solutions? So if I continue the question, so would you do this every time, or do you anticipate some kind of regime or look up the dictionary? So do you thought about something like that?
That's a great point. That would help solve that problem if you were able to form some kind of lookup table for different flow regimes, calculated a de Rosier for different flow regimes. Like for the AERIs, we could calculate one for cloudy retrievals versus clear retrievals, and then use an error profile unique for those two. Because that seems to be one area where the AERIs have a lot of issues is with the cloudy retrievals. So you could do that to solve the problem by just separating this into and getting a static error profile, but based on different regimes.
Okay, so there's another question by Daniel Leuenberger from Meteor Swiss. He asked, could we try to just take the term from the last cycle instead to compute it for the current cycle?
Take the term from the last cycle and compute it. I'm not sure I understand the question. Are you talking about using the de Rosier?
Yes, he's talking about the de Rosier.
Okay. I'm not sure if that would be. It depends on your cycling frequency. The convective scale, things can change very rapidly on the order of minutes. Convection or changes on the order of minutes. So you really have to balance that out with your cycling frequency. If you're doing hourly cycling, then no, I wouldn't recommend using the previous cycle because clouds could roll in very quickly and that could degrade some of your retrievals. But if you're doing very rapid cycling, then yeah, that would be an option.
Okay, so I think we need to move on. So there are some more questions in the OPAD. So Samuel, if you want to answer them in written form, please do that. I think perhaps there are coming even more questions. It was a really interesting talk. And yeah, let's move on to the third presentation.